Well, thank you very much for inviting me to this great meeting. Great pleasure to be here. My name's Steve Harridge. I'm Professor of Human Applied Physiology at King's College London. I'm going to be talking about ageing, a topic close to many people's hearts. First of all, I'm going to start with acknowledgement. This is my good friend and long-term collaborator, Professor Norman Lazarus. So in addition to him being a scientific investigator with me, he is also one of the participants in our ageing studies. He's a very keen long-term cyclist. And I'm also going to declare a conflict of interest. This is a marathon meeting. I've never run a marathon. I don't intend to run a marathon. This was me back in 1979, just to show my ageing trajectory. This is me in 1985 on the same athletics track. And just at the end of last year, I revisited the same athletics track to see how my performance was declining. But I'm a passionate advocate of exercise, and in the context of ageing, it is essential. We're all living longer, but to an unhealthy old age. This is a great piece from the newspaper a few years ago that I took. And it's really important. So the good news is we're living longer. The bad news, we're not living healthier. So we have this increased lifespan. We don't have an increased health span. So how do we study the biology of ageing? So obviously, huge area of research that's ongoing at the moment. We look at different cells, different tissues. There's a whole series of hallmarks of how the body's looking to age. So we can spend the whole hour discussing inflammation, cellular senescence, and so on. I'm not going to touch upon that, but it's an area that we are looking at and using exercises to do that. I'll come to that towards the end. But let's look at some simple graphs as regards aging. Let's take muscle function. I'm a muscle physiologist by training and interest. Let's take muscle function plotted against age. What happens? Well, what happens is we're born, we grow, we reach some kind of peak in adulthood, and then there's this progressive decline as we get older. And what I put in here is this gold line. This gold line is the threshold for independence. This is the amount of muscle function, whether it be muscle strength, muscle power, they're not the same things, that you may need to do a simple physical task, such as rising from a chair unaided. And there'll come a point where you'll lack the capacity in skeletal muscle function to be able to do those things independently. Many people are just about okay, but they're hovering, and they may have a trip, a stumble, a fall, break a hip, and now on this trajectory below that threshold, many lose independence. And of course, I don't know, from Alistair's talk, we know that many people undergo hip surgery, and of course, many people don't survive. And of course, that accounts for billions of pounds worth of NHS. So we have just a simple problem that just derives from this simple fact, which is highly related to this skeletal muscle function. But if we want to study aging, we understand the biology of aging. Who do we study? So many of you may recognize this particular individual from the royal family. Now, is this a model in someone who you will study aging processes? And I will say, no, this individual isn't a model that you want to study biological aging, because you've got an individual who's doing no physical activity, they're eating poorly, they're smoking, they're drinking to excess. These are things that are all negative lifestyle features for your physiology. So when you measure and study people like this, you're not looking just at aging, you're looking at all the other factors in addition to them getting older. Now, at the other end of the continuum, we have, as people in this audience well know, people who still do this, who are competitive athletes. Now, unfortunately, from our point of view, most studies of aging tend to be more clinically focused and are driven towards this end of the spectrum. What can we do about all these people here, rather than studying people on the left-hand side, which is actually how do we understand what's happening to the body as we age under the most optimal conditions? What do we know? What can we aspire to when we're 80 and 85 in terms of our physiological function? We don't really know. So inactivity, it's deleterious to our health at any age. So when we study inactive people, it's really contaminating our understanding of biological aging. So we kind of put a health warning, if you like, on many studies of aging, because we're not studying just biological aging, we're studying aging and inactivity. And Norman and I have written a number of articles around this particular topic. Now, let's go back to athletics and performance. So what we've got here is a range of distances from sprinting through to 400-metre hurdles, my own distance, right up to the marathon. To look at the challenges that those events face. They're very, very different. Both mechanically, metabolically, they're very, very different, as reflected by the average running speeds for the world records given there. But what's interesting is in terms of the aging decline, the shape of the declining curves is quite similar, irrespective of the event. And these are quite interesting when we study world records, because the phenotype of a sprinter is different to the phenotype of a marathon runner. So what we've got here is a quote from a Nobel Prize-winning physiologist from UCL, A.V. Hill. In the study of physiology of muscular exercise, there was a vast store of accurate information in the records of athletics and racing. He said that back in 1925. So now we're looking at this and applying it to aging. So these are the Masters world record performances. So in Masters athletics or Masters events, we go in 5-year age increments. And what you're looking at there is the 10,000 meters on the track. I prefer to use this rather than marathon data, partly because you've got the same track. It's much more standardized. But you can see there's this progressive decline in performance every 5 years in both males and females. You get to around 70, 75, and then it really starts getting a lot worse. If we look at the 100 meters, a sprinting event, we actually get a similar phenomenon. We get this progressive decline over time, and then an acceleration around 75 years of age. So there's lots of information, interesting data talking about aging, because ultimately you can argue that athletic performance, whether it's running a marathon or it's sprinting, is the ultimate integrative physiological function. Everything has to be working really, really well. Cognitive function, cardiorespiratory function, neuromuscular control, metabolism, all has to be working to deliver these hardcore performances. So the best performances ever recorded, it's all declining. It's progressive. But this is, you can argue, biological aging. We can apply that to swimming, similar kind of thing. The data are expressed slightly differently for swimming world records, but again, males and females, sprint and long distance activities, similar kind of thing, progressive declines, plotted in a slightly different way, but now you're looking at this break point again at around age 70, where it gets a whole lot worse. Okay, so let's come back to some basics of physiology and metabolism. When we're doing high intensity exercise, we're looking at supplying our muscle through phosphocreatine, the breakdown of glucose via glycolysis and phosphocreatine and so on. But then we start undertaking our endurance activities. We're using aerobic metabolism, the oxidation of fats and carbohydrates and so on. So when we come to our marathon events, we're really back to this massively and beautifully integrated physiological system, where ultimately we have at the left-hand side our mitochondria, which are acting as the final electron acceptor in the respiratory chain to produce ATP from aerobic metabolism. How do we get that oxygen in? We take it in from the atmosphere. We need a great set of lungs to take in that oxygen, to diffuse into the circulatory system. We've got a heart and a series of great blood vessels to deliver that oxygenated blood to the working muscles where it's needed. And what we don't even think about is how that's regulated. The fact that we increase ventilation, we increase our cardiac output to match the working requirements of the muscle. We don't think about it, but it's a fantastic piece of design. So if we just do a simple bit of physiological data, we've got a graph here, we've got workload on the bike, increasing your power output or increasing your running speed. What happens to the oxygen cost, your VO2? It goes up and it reaches a point of maximum, your VO2 max. If we were to take a capillary blood sample and measure the concentration of lactate in the blood, you'd see that that stays quite stable until you reach a certain point, and then it suddenly starts getting a lot higher, and that marries up to carbon dioxide production and increased ventilation that's occurring, and this is what we commonly term the anaerobic threshold, and that's an important point to note, because this is one of the key features when we look at what makes a great marathon runner from a physiological perspective. We work from the bottom up. We've got your maximum velocity in a distance race, your velocity at lactate threshold. Now, how quickly can you run before you start accumulating lactate? Well, what feeds into that? Your maximal oxygen uptake. What feeds into your maximal oxygen uptake? Well, your cardiac output, your ability to extract oxygen, what feeds into your velocity at lactate threshold, also the percentage of your VO2 max before that occurs, and your running economy. So we can dissect some of these out and apply them to aging. But Mike Joyner, who's a fabulous physiologist and an anaesthetist actually from the Mayo Clinic, he predicted back in the early 1990s the first sub-2-hour marathon would occur. And he based that on, if I take a really high level VO2 that we might expect from some of the top athletes. So a VO2 max of around 84 mils per kilo per minute. A lactate threshold occurring at about 85% of VO2 max, and an exceptional running economy. Put all those things together to create the perfect athlete, then you'd get something in the region of 1 hour 58 minutes for the marathon. And that's pretty much what was achieved by Eliud Kipchoge a few years ago, first sub 2 hour marathon. So what's happening in aging? Well, before we do that, let's look at the relevance for VO2 max. How does it relate to our performance? Well, if you take a whole bunch of marathon runners and plot their VO2 max against performance time, you can see that there's an inverse relationship. The higher the VO2 max, the quicker you're going to run. And I've taken these data specifically from this marathon medicine book, which was from the meeting in 2000, which was edited by Dan Tunstall-Pedo. I was at that meeting, and fantastic speakers then. And this is a paper from Bengt Saltin's group showing this relationship. So what is VO2 max? I'll come back to the importance of VO2 max a lot. It's the maximum rate at which we can consume oxygen during whole body exercise. You can call it aerobic power, aerobic capacity, cardiorespiratory fitness. This is what it basically is. And high levels are typically associated with endurance athletes. And you're seeing on a graph on the right where you've got work rate on a bike, increasing work or exercise intensity, and on the left or the right-hand side, you've got maximal oxygen uptake in litres per minute, then divided by your body weight to create mils per kilo per minute on the right-hand side. And you can see the progressive rise in VO2 as you go towards the endurance-trained athletes. But from a public health perspective, your cardiorespiratory fitness, your VO2 max, is arguably the best predictor of your all-cause mortality. It's a fantastic biomarker. If you can measure one thing in someone, I'd measure their VO2 max if I could. So let's go back to something that's public health related then, and because I'm in London and it's the marathon and we have lots of London buses, let's pay due respect to Jerry Morris and this classic study that was done back in the 1950s, which has really paved the way for all the physical activity type studies that have come subsequently. And he basically studied London bus drivers and London bus conductors. And basically what he did was identified that the rate of myocardial infarction, or the incidence of myocardial infarction, was double that in the bus drivers relative to the bus conductors. So a really nice environment. They're in the same environment, okay? But one's walking up and down stairs all day, and the other's sitting there driving. So this is the key observation of what much of our sort of public health and exercise epidemiology is based. More recently, and this is a summary of lots and lots of other slides, what do we know? We know that as you decrease your levels of cardiorespiratory fitness, or VO2 max, that's shown in the blue, you increase your risk of mortality. Decreasing levels of moderate to vigorous physical activity, also bad for you. Increasing the time spent sitting, so increasing your sitting time, shown in brown, shown in amber, is also declines. All this is painting a picture of the importance of physical activity, cardiorespiratory fitness for general health and in respect for all-cause mortality. So this vitally important VO2 max then, what's determined it? What is the determinant of your individual VO2 max? It's essentially your maximal cardiac output. That is the best correlate with your VO2 max. Now, when we get into the detailed physiology, and this is Bengt Saltin, who is I had the privilege of working for him for 3 years in Scandinavia. He had this model, which is a bit more extreme than your typical exercise physiology lab, where you would catheterize the femoral artery and vein, and you'd measure the VO2, the oxygen consumption, across a working limb. And when you do that, you can see that actually you're not limited by your cardiac output. So the muscle has the capacity to take more oxygen. It's just that when you're doing whole body exercise, you've got to share that oxygenated blood around the rest of the body. So what happens to a VO2 max as we age? Well, I'm going to show you data from our own study. So our own study, we've been very interested in using Cyclist, we've just chosen Cyclist, as a model to study healthy aging. Pragmatically studying cyclists, okay? So we took 9 years ago, a group of people aged 55 to 79 years of age, brought them to our laboratory for 2 days of detailed physiological testing, including measuring their VO2 max. quite strict entry criteria. You had to be able to cycle 100k in under 6.5 hours if you're a male, etc. And the data I'm showing you here is the simple relationship between age and VO2 max in litres per minute. Okay? So no surprise, it goes down with age. Well, we knew that already. Okay? I know we knew it goes down with age, but in this study, what we've done is remove the confounder of inactivity. These are all highly active people. They're all doing the same type of exercise. So it's a really nice model for studying aging. The females that are shown in the dark, the black circles, are lower. They have a lower skeletal muscle mass, less ability to consume oxygen. So what we can do is normalize that typically to mils per kilo per minute. The lines become slightly closer together. But what I'm doing here is adding in for context the slope of a line from a meta-analysis plotting sedentary males against age in terms of their VO2. So let's, for fun, say, well, let's take an 80-year-old cyclist and see where they hit that sedentary curve. Well, they hit it at age 45. So you say, wow, this is great. This is a 35-year functional advantage. What I'm going to do is challenge the perception of that. It's not a 35-year functional advantage. It's a 35-year functional disadvantage for the sedentary people. So from an evolutionary biology perspective, our bodies were designed to move, to be physically active. The cyclists are where they should be. The sedentary people are not where they should be. So those are the people that are not the norm, okay, from a biological perspective. So it's a 35-year functional disadvantage. We can also take it a step further and normalize to fat-free mass. We can do a DEXA scan, normalize to essentially lean tissue mass, which we've done here. Now the sex difference has disappeared. In fact, the two best performers in terms of VO2 max at the young and at the older end of the spectrum are in fact females. Let's do another thing. Because we're interested in, and you hear a lot in the news, biological age. What's my biological age? Okay, I struggle with this biological age concept. I'm taking these data between those two red lines, creating a little bandwidth of function, and I'm replotting that data. So now we've got VO2 on the x-axis and age on the y-axis. It's the same data plotted. Okay? All this is saying is that with quite a narrow band of VO2 max, I could be aged between 55 and nearly 75. Okay? So the point being, humans are really heterogeneous. We're all very different and can still be quite normal within quite a range of values. So, it's going down with age. This is important for performance. So what's going on? Well, our maximum cardiac output is going down, primarily driven by reducing maximal heart rate. Your maximal heart rate decline is a biological function of age. That is not manipulated by your exercise status. We're also declining and losing our muscle mass. These all contribute to how many litres of oxygen can you consume. But let's talk about muscle mass. My favourite topic is skeletal muscle. What you're looking at here is the MRI of midsection through a thigh of a 31-year-old female and an 85-year-old sedentary female. And what you can see straight away is that you've got in the lower image, you've got less dark material, which is the contractile tissue of the muscle. You've got more subcutaneous fat wrapping around the muscle, and you've got an infiltration of fat and connective tissue within the muscle, and you've got overall less skeletal muscle mass. When certain thresholds for function and mass are reached, we have a disease process called sarcopenia. If we look at sarcopenia in a bit more detail, if we take a muscle biopsy, for example, and look at the histological profile, we're now looking at a healthy young muscle on the left. This is a nice bad example, an extreme example on the right of an older muscle. The muscle fibers are now different shapes, different sizes. You've got infiltration of fat, of connective tissue shown in green. The red is showing fat accumulation. Really poor quality. What we also have is a picture that's missing. That's meant to show you some muscle fibers that are getting smaller in older age. So our type 2 fast contracting fibers atrophy, and we get a total loss of skeletal muscle fibers. So you see, well, how much of this is aging and how much of this is inactivity? Because muscle is a tissue which is exquisitely sensitive to activity, to mechanical signals, to metabolic signals. So this whole business about understanding aging, well, if we're studying a disused, inactive older person's muscle, how much is it because it's old? How much is it because it's inactive? So when we look at some MRIs in our master cyclists, for example, this is an 83-year-old master cyclist, that's not a sarcopenic muscle. What else happens as we get older? We've just finished studying our cyclists 9 years later. So the hypothesis being, if we follow up a cyclist, they've been exercising for 9 years, they're still healthy, if we see a change in them, that we can really attribute that to a proper biological aging process. So what we've seen is an unchanged body mass, but a decrease in lean tissue mass and an increase in fat mass. Something we kind of knew was happening generally among older people, but how much of that could we ascribe to biological aging? So that's going to have an implication for when you're running, because what you're carrying and what's ultimately reflected is your VO2 max relative to your body mass. So, we said there's a great correlation between VO2 max and your performance time when we look at across a wide range of individuals. But in this paper by Venk's group, what they did was said, well, let's look at the relationship between marathon performance and VO2 max across some top competitors. And here you can see we now have an uncoupling of that relationship. There is no correlation between VO2 max and age. So now we're into the realms of what does best predict your VO2 max. We're back to that indice, which is your lactate threshold. And we've known for a number of years that if we look at the velocity at your anaerobic threshold against the marathon velocity, beautiful relationship. And again, from that paper, from the meeting in 2000, this is a really nice little study. The 10-kilometre run times, the top 10 Kenyan runners, shown here, measured 3 days after competition in a laboratory to see what their lactate threshold was. And you can see the better competitors are the ones that have the lactate threshold pushed to the right. So this VO2 max at which lactate threshold is occurring, really important. And I'm just going to do a sidetrack because there's always an interesting case report. This is the New England Journal of Medicine a few years ago, top medical journal to get into, very difficult to get published in, again from Mike Joyner's group. And this showing a 70-year-old marathon runner, broken the age world record. And what was really interesting is the middle graph. It's difficult to see, but actually his lactate threshold was occurring at 93% of his VO2 max. Now, in Mike Joyner's model, he said, I've taken the best value as 84%. And here you've got an older athlete performing at a remarkable position, even though his VO2 max may not have been completely exceptional. So when we come into looking at what then determines our lactate threshold, this schema says, well, now we're looking at local things within muscle. You're looking at the local perfusion, the capillary density, and you're looking at oxidative enzymes within the muscle, your mitochondria, which is then basically leading on to fiber type. So fiber types, another interesting lecture that we can have about our fast and slow twitch fibers that we tend to think about more crudely, but essentially in humans we have 3 types of fiber: the type 1 slow fiber, then the type 2 fast fibers, which are subdivided into type 2A and type 2X, and that's based on the left-hand side on the basis of the molecular motor, your myosin crossbridge. And it's quite a cool experiment just shown on the left there. What you're looking at here are some actin filaments that have been taken from a muscle biopsy sample, being moved around on a microscope slide by myosin crossbridges that you can't see. So these little worms are moving actin around. We can measure the speed of motility and basically show 2X molecules move quicker than 2A molecules and type 1 molecules. So what you're also seeing here is our mitochondria. Our type 1 fibers are packed full of mitochondria relative to our type 2 fibers, and our type 1 fibers tend to be better perfused and so on. And what you're looking at there is quite a nice just image where we take a muscle biopsy sample, a typical quadriceps muscle. We have a mixture of fast and slow fibers in the main, but if we were to take a group of marathon runners, they will be skewed towards the type of having a distribution of more type 1 muscle fibers. So if we study our older athletes or our older cyclists, what's going on? Well, the 55-year-olds, 65 and 79-year-olds, the muscle's great. There's no problem with that muscle. We didn't see an association between fibre type composition and age, or indeed fibre size and age. So we seem to be having a really good maintenance of muscle quality, even if overall the size of the tissue is poor. Quick word about capillarity. This is measuring the capillaries in our muscle fibres. Essentially no association between age and capillary number. In other words, the muscles of the older individuals who are exercising is still fine. But a typical view of aging muscle is it's less well perfused. Well, is it less well perfused because it's inactive? Same with our mitochondria, measuring the different complex proteins within the mitochondria. Lots of noise, no association with age. And this is not our data, but it's a nice study which kind of depicts what a typical view of aging would be. Your mitochondria are not functioning as well as you get older. So here we've got on the left, on the open symbols, the young individuals, some older sedentary people. Doesn't matter what they are, so mitofusin 1, for example, are involved in mitochondrial fusion and so on and so forth. Doesn't matter. The point I want to show you is it's going down. That's the typical view. But when in this study they studied exercisers in red, you can see it's not going down at all. In fact, the older exercisers are better than the young non-exercisers. So your interpretation of an aging effect could be completely different if you hadn't really classified exactly who you were studying. Studying sedentary people, it goes down. Studying exercisers, well, it goes up. Well, in reality, the key thing they're missing here in this group is the young exercisers, because that would be the true aging change, going from a healthy, exercising young person to a healthy, exercising older person. Okay. But last part. Do we need to run marathons to age well? How much is enough? Key question. I'm obviously not going to age well if I don't run a marathon. You don't need to run a marathon to age well. So this is a set point theory that Norman and myself came up with a couple of years ago, which is saying there is a certain amount of exercise that we all need to do that keeps us healthy and will allow us to age optimally, to optimize our health span, to compress our morbidity at the end of life. And we'll have a discussion about how much that might be later. The athletes are here. They're doing more than you need to do. Are they aging any better? It depends what you mean by aging. Like anybody at any age, they still have the capacity for improving their performance. They can get better. Okay? But are they aging any better? No. Maybe their health span should still be optimized, assuming no overtraining pathologies. Okay? But these aren't the problems. Just to show you a bit more about that set point theory. So this is age on the x-axis, level of physical activity on the y-axis. It's showing that over time, the amount of exercise you need to do to remain healthy declines as you get older. In absolute terms, it's declining as you get older. Okay? And we kind of know that. As a 400-metre hurdler, the athletic events have accommodated me getting older. When I turn 60, it's no longer 400-metre hurdles, it's 300-metre hurdles. And the heights have got lower. Okay. Thank goodness. Okay. So it's accommodating. Okay. So are we expecting someone who's 90 to be able to train like they were then when they're 20? Common sense is not really possible. Okay. But what that 90-year-old might be doing might be the same relative intensity relative to their age. But this is the problem. This is the problem. The people in the red group who are not doing enough. And of course, that's the vast majority of the population. So now you've got aging interacting with inactivity, so we don't know what's going on as regards aging. And we could put it on that scheme here. We've got an uncertain health trajectory and decline. But what certainly we're going to have will be a more extended period of morbidity. So our aging research has been focused essentially on that by studying our cyclists. They're above the red zone, they're in the green zone, and maybe in the gold zone, some of them. So our current project, and I've got no data, we've just literally finished testing nearly 200 people. We're testing young cyclists and old cyclists, the group I've just shown you. Young inactive people, old inactive people. So we've got this matrix of age and inactivity. So that's the research team I'm showing you there. But what are we doing? So I mentioned those hallmarks of aging. So they come to the laboratory for 2 days, and we are doing lots of physiology, capturing their physical activity and so on. We're doing a lot of muscle biology, but we're also doing this huge multi-omics. So the technological advances over the last few years allows us to study so many things. So they come in and give us a skin biopsy, a fat biopsy, a stool sample, a blood sample, saliva sample, a skin sample. So we're doing this deep biological phenotyping of them, with the whole arching hypothesis being, if it's truly an aging effect that we're measuring, whatever it may be, it should be in the exercises and the non-exercises. If it's not, in other words, it's a feature which is massively affected by exercise, VO2 max, then we're not looking at just a purely aging phenomena. We're looking at an interaction of aging and inactivity. So we take one of those features, these are data from our original study, inflammation. Many older people are in a chronic low-grade inflammatory state. That's depicted in the black versus the blue bar, from a young to a healthy older population, healthy but inactive, in terms of IL-6 and TNF-alpha, two inflammatory cytokines that are typically measured. But you can see the cyclists that we're studying in the red bar are completely different to the sedentary, inactive older people. So inflammaging in this instance, say, well, that's inactivity then that we're looking at. So just a taste of the kind of things that we can look at. So in summary, our physiology declines as we get older. That's biological fact, I'm afraid. In most older people, there is an interaction of aging and inactivity processes. If we want to understand just the biology bit of the aging bit, we need to study people who are exercisers. Exercise does not prevent or reverse aging. You say, well, I didn't do anything before, now I'm 65 and I started running, I'm younger. Well, no, what you've done is reverse all the deconditioning problems you had. You haven't reversed your biological aging. You've put yourself on a much better slope. But performance declines as we age. So this leads to this question which I'll end on, which is, as an older athlete, who are my competitors? Not your younger self. And there's lots of discussion to be had about, next year I'm going to do this, the year after I'm going to do that. But you're on a slope of decline. So you're all going to get slower over time. If you're starting off, each year you're doing your optimal, you will decline. That's, of course, a big question for discussion. Not your younger training partners. I've got to keep up with the guys who are 20 years younger than me. Why? You haven't got that physiology anymore. Your competitors are your age-matched peers. So with that, I'll acknowledge the research team, some of the data I've been showing you today, and thank you very much for listening.